Welcome to this workshop on meta-analysis. This video is one in the series, and I recommend this one if you plan to work with the risk of an event in one group. For example, prevalence or incidence. This video includes both a basic section and also an advanced section. I'll cover the following items: how to enter data, how to run the analysis, how to estimate the mean effect size, how to understand heterogeneity in effects, how to report the results, and how to create plots. I'll also cover the following topics: how to perform a subgroups analysis, how to perform a meta-regression, and how to assess the potential impact of publication bias. I'll be using the software Comprehensive Meta-Analysis, or CMA. Our website is metaanalysis.com. There you can download a free trial of the software and also the datasets used in this video. This analysis is also discussed in our text, Introduction to Meta-Analysis, 2nd edition, and in our book, Common Mistakes in Meta-Analysis and How to Avoid Them. The analysis includes 25 studies that look at the short-term risk of death for patients in their 80s or older who undergo mitral valve surgery. That is, surgery to repair or replace the mitral valve in the heart. Each study reports the number of patients enrolled and the number of patients that died either during surgery or shortly thereafter. There is no comparison group. We simply want to know the risk for patients in this age group. The effect size index is the risk or the incidence. This example is based on data from a systematic review that was published by Bianchari et al. In 2013. If you're interested in the specifics of this analysis, please do not rely on this video, but consult the original paper. Let's look at the data first in Excel. The file is called mitralvalve.xls. There's a column here with the study names. There's a column with the number of patients who died, and a column with the total sample size. There are also some columns with potential moderating variables. We'll discuss these later. I want to copy this data into CMA. I'll highlight all the relevant cells, and notice that I'm including the row with the labels. I click Control-C to copy. I'll open CMA. I'll close this box. I click in this cell, and I click Control-V to paste. Next, I want to take these labels and move them into the header. I click Format, First Row as Labels. At this point, the labels are correct, but I still need to identify the function of each column. On the menu, there's a button that I can use to insert columns, and there's a separate button that I can use to identify the function of columns that already exist. Since the columns are already in the grid, and I want to identify their functions, I'll use Identify rather than Insert. I click on the first column, then I click Identify Column for study names. The program changes the header to Study Name. Next, I click Identify Column for effect size data. The program opens this wizard. CMA will accept data in many formats, and so I need to tell the program which format I want to use. I also have the option of entering data for some studies in one format, for other studies in a second format, and so on. At the bottom, I choose Show All 100 Formats, and I click Next. The first button is for formats that compare the events in two groups. The second button is for formats that report events or means in one group. I choose that and click Next. On this frame, I choose dichotomous number of events because I'll be looking at the number of events. Then I choose raw data, and under that, I choose events and sample size. If I were inserting these columns, the Finish button would light up. Since the columns already exist and I need to match each column with its function, the Next button lights up. I click Next. I need to identify the column that holds the number of events. I click here and I select Events. That's the label that had been used in Excel and then moved into CMA. I need to identify the column that holds the sample size. I click here and I select Sample Size. And finally, I click Finish. The program has now created a set of columns to hold the data. These columns are labeled Events and Sample Size. The program computes the effect size for each study and displays that here. This column shows the event rate. The first study had 2 deaths out of 10 patients, so the event rate is 0.20. This column shows the event rate in logit units. To perform the analysis, the program will convert the event rate into logit units, perform the computations, and then convert the results back to event rates. This is all done automatically, and you don't need to think about it. However, if you do want to be able to follow the computations, you would need to use these values. To modify the display, I can right-click on the yellow columns, and I click the option to customize the display. The program opens this wizard. By default, the program has checked the 2 effect size indices that we just discussed, the event rate and the logit of the event rate. If I wanted to hide the logit, I could uncheck this box. At the bottom, I check the option to show the standard error, and I check the option to show the variance, and then I click OK. Now the program is displaying the standard error and the variance for the logit value. These values are not displayed for the event rate itself. I will also need to assign a function to these other columns. I'll come back and do that later. This would be a good time to save the file. I click the Save icon and I give the file a name. Before I leave this screen, let me point out 2 things. If I wanted to see the formula that was used to compute the effect size, I could double-click on any cell and see the formula. Also, in this analysis, all studies reported data in the same format, but I also have the option to mix and match formats. For example, if some studies had reported the event rate and sample size, I could work with that. The program would take the data as entered for each study and use the appropriate formula to compute the effect size and variance for that study. Then all of the studies, regardless of their original format, could be included in the analysis. I click Run Analysis. Here, I can select an effect size index. I'll be using the event rate. These columns show the statistics in numbers, and these are also plotted here. At the bottom of the screen, I can choose either the fixed effect model or the random effects model. I choose the random effects model for 3 reasons. First, it allows me to take account of the study-to-study variance when assigning weights to each study. Second, it allows me to assess the dispersion in effect size across studies. Third, this model will allow me to generalize from the studies in the analysis to the universe of comparable studies, which is what I intend to do. Next, I'd like to set the scale for the forest plot. I right-click on the plot, I select Scale, and I set the scale to go from 0 to 1. I'd like to sort the studies by effect size so that I can get a general sense of how widely the effect size varies across studies. I right-click on the column labeled Event Rate. I click Sort from Low to High. I get the sense that the effect size in most studies falls in the range of around 2% to 30%, but there are a few studies with effect sizes outside that range, including some as high as 50%. In any event, this is only intended to give me a general sense of the dispersion. We'll compute the actual dispersion momentarily. If we were looking at a difference between groups, the program would display the z-value and the p-value for a test of the null hypothesis that the risk is the same in both groups. However, since we are looking at the proportion in one group, we're not testing any null hypothesis about the risk, and so these columns are not displayed. Each row displays data for one study, and there are two rows for the summary effect here and here. To understand what these rows tell us, let me take a step back and explain the goal of a random effects analysis. When we perform a random effects analysis, we assume that there is a universe of potential studies that we care about. In this case, it might be all studies that could be performed to assess the short-term risk of death from mitral valve surgery in patients older than 80 years. I'll refer to this as the universe of comparable studies, or simply the universe. We assume that our 25 studies are a random sample from that universe, and therefore we can use these studies to make an inference to that universe. The initial analysis has two goals. The first goal is to report the mean effect size in this universe. The second goal is to report how widely the true effect size varies across studies. With that in mind, let's have a look at the analysis. This line gives me the mean effect size. The mean event rate is estimated as 0.166. The confidence interval is 0.142 to 0.193. In round numbers, the mean is 17%, with a confidence interval of 14% to 19%. That tells me that in the universe of comparable populations, the true mean probably falls in this interval. However, all of this deals only with the mean. It's equally important to understand how the event rate varies across studies. The dispersion is addressed by this line, which is called the prediction interval. It tells us that in 95% of all comparable studies, the event rate is expected to fall between here and here. This is addressed in more detail in the section that follows immediately. If we look at the plot of observed effects, we see that at one extreme, there's a study where the event rate is around 2%, and at the other, there's a study where the event rate is around 50%. To be clear, though, we do not want to simply report the lowest and highest effects that we see here. If we did that, we would be basing our results on two studies and ignoring the information in the other 23. Additionally, the event rates that we see incorporate some amount of sampling error. The event rate in this sample is 2%, but the actual event rate in that population could be as high as 11%. So, to compute the actual amount of dispersion, we do something similar to what we would do in a primary study. We compute the standard deviation of true effects based on the information from all 25 studies. Then, we compute an interval based on the mean plus or minus 2 standard deviations. If we can assume that the effects are normally distributed in the relevant units, we would expect that the true effect size in 95% of all comparable populations will fall within that interval. Before I explain how we do that, I want to address two common mistakes. Some researchers think that the confidence interval tells us something about the dispersion in effects. For example, they might think that the effect size in individual studies ranges from here to here. And that is completely wrong. The confidence interval is an index of precision, not an index of dispersion. It tells us how precisely we've estimated the mean. It says nothing about how widely the effect size varies. A second common mistake is that people think that the I-squared statistic tells us how much the effect size varies. While this is a very common mistake, it is still a mistake. The I-squared statistic does not tell us how much the effect size varies. I discussed this in other videos and papers. For now, I'll simply make the following point. In this analysis, I-squared is 63%. On that basis, how much does the effect size vary? And the answer is that there's no way to know. The I-squared statistic simply does not provide that information. In a variant of this mistake, researchers sometimes use I-squared to classify heterogeneity as being low, moderate, or high. These classifications are meaningless for two reasons. First, they're based on I-squared, and I-squared does not tell us how much the effect size varies. It follows that any classification based on I-squared also cannot tell us how much the effect size varies. Second, the classifications are not informative. For example, what does high heterogeneity mean? Does it mean that there are populations where the risk is as high as 30%? Or does it mean that there are populations where the risk is as high as 50%? Or does it mean that there are populations where the risk is as high as 70%? There is no answer. The idea of classifying heterogeneity using these terms is simply not useful. So, what statistic does tell us how much the effect size varies? That statistic is the prediction interval, which is displayed on this row. The prediction interval is 0.097 to 0.269. This is also plotted here. In round numbers, at one extreme, there are some populations where the risk of death is as low as 10%, and at the other extreme, there are some populations where the risk is as high as 27%. Why is this called a prediction interval? Well, suppose that someone needed to decide whether to undergo this surgery. If they survive the surgery, their long-term prospects are good, but they need to balance this against the short-term risk. They asked me how likely it is that they would die as a result of the surgery. I would predict that their risk would fall somewhere between here, and I would be correct for some 95% of all populations. To recap, these two lines address two distinct issues. This line deals with the average effect. The average effect falls someplace between here and here. This line deals with the dispersion in effects. In any single population, the true risk could be as low as this or as high as this. I can also create a high-resolution version of this plot. I'll discuss later how to create this plot, but right now I want to show one thing. These two rows are the same as the ones we saw a moment ago. This row displays the mean effect size and its confidence interval. Here, the confidence interval is displayed using a horizontal line as it was in the prior plot. We can also display it using a diamond, which is a common convention. But whether we use a line or a diamond, the meaning is the same. This line represents the confidence interval. It tells us how precisely we have estimated the mean. It says nothing about the dispersion effects. For dispersion, we turn to this row, which displays the prediction interval. In any single population, the true risk will usually fall between here and here. CMA can also create a second plot, which takes the information in these two rows and presents it in a more intuitive format. If I click this button, the program generates this plot and these captions. This caption corresponds to this line. It reads, the mean effect size is 0.17 with a 95% confidence interval of 0.14 to 0.19. This caption corresponds to this line. It reads, the true effect size in 95% of all comparable populations falls in the interval 0.10 to 0.27. The prediction interval, 0.10 to 0.27, reflects the endpoints of this distribution. And this is a useful way of summarizing the plot. But when it's possible to display the entire plot, we should do so, since it provides a more nuanced look at the distribution. The prediction interval told us that there were some populations where the effect size was as low as 0.10 and others where it was as high as 0.27. By contrast, the plot gives us a more detailed view. For example, I can see that in most populations, the risk falls somewhere between here and here. In only a relatively small number of populations does the effect fall in this range or in this one. Finally, I can edit the title, and I can send this to Word or to PowerPoint. For additional details, I close the plot and I click Next Table. This screen is divided into two parts. The left side of the screen deals with the mean effect size. The right side of the screen deals with heterogeneity. I'm going to use the statistics for the random effects model, and these are the same statistics that we saw on the prior screen. Here are the mean and its confidence interval. Then let's look at the heterogeneity. For heterogeneity, some of the statistics are reported on this row and some are reported on this row, but they all apply to the random effects model. Here we have the Q value along with its degrees of freedom and p-value. Here we have tau and tau squared. Here we have the I-squared statistic, and here we have the prediction interval. If you'd like to learn more about these statistics, these are discussed in our book, Common Mistakes in Meta-Analysis and How to Avoid Them. You can download that book for free on our website. But for now, I'll only make the following point. Each of these statistics addresses a specific question. We need to be clear about what question we intend to ask, and then we need to apply the appropriate statistic. One question we can ask is, does the true effect size vary at all across studies? For that, we turn to the Q value along with its degrees of freedom and p-value. If the p-value is less than the criterion alpha, we conclude that the true effect size does vary across studies. The criterion alpha for testing heterogeneity is sometimes set at 0.10 rather than 0.05. So any p-value under 0.10 would be considered statistically significant. In any event, the Q value is 65.668 with 24 degrees of freedom and a p-value of less than 0.001. In other words, there is empirical evidence that the risk of death is higher in some studies than in others. The second question we can ask is the following. What is the standard deviation of true effects, or what is the variance of true effects? These values are given by tau and tau squared. Since the analysis is being performed using a logit transformation, these values are presented in logit units. The standard deviation of true effects, tau, is 0.282 in logit units. The variance of true effects, tau squared, is 0.080 in logit units. A third question we can ask is the following. The dispersion that we see in the forest plot is partly due to variance in true effects and partly due to sampling error. So we can ask what proportion is due to variance in true effects. And that question is addressed by the I-squared statistic. In this case, I-squared is 63.453% or 64%. This tells us that 64% of the variance that we see reflects variance in true effects. The other 36% is simply sampling error. Note that 64% is a proportion and not an absolute amount. It tells us what proportion of the variance reflects variance in true effects. It does not tell us how much variance there is. The fourth question we can ask is the following. What is the range of true effects? Or, if I were to pick one population at random from the universe of comparable populations, what would the true event rate be in that population? That question is addressed by the prediction interval. In 95% of all populations, the true risk falls between 0.097 and 0.269. In round numbers, between 10% and 27%. In practice, papers typically report the Q value along with its P value, and they report tau squared and I squared. A common mistake in papers that report a meta-analysis is that these statistics, especially I squared, are interpreted as telling us how much the effect size varies. However, this is incorrect. These statistics do not tell us how much the effect size varies. That question is addressed only by the prediction interval. There's one very important caveat to all of this. In order to estimate heterogeneity reliably, we need a minimum number of studies in the analysis. The number of studies needed will vary based on several factors. However, we might use 10 as a useful minimum to provide a sense of scale. When the effect size varies substantially across studies, and there are less than 10 studies in the analysis, we cannot have confidence that any of the statistics related to heterogeneity will be reliable. This includes I squared and tau squared, as well as the prediction interval. CMA is able to generate a report that explains the meaning of all the statistics. I click here to generate that report. The report reads as follows. Overview. The analysis is based on 25 studies. The effect size index is the event rate. Statistical model. The random effects model was employed for the analysis. The studies in the analysis are assumed to be a random sample from a universe of potential studies, and this analysis will be used to make an inference to that universe. What is the mean effect size? The mean effect size is 0.166 with a 95% confidence interval of 0.142 to 0.193. The mean effect size in the universe of comparable studies could fall anywhere in this interval. The Q test for heterogeneity. The Q statistic provides a test of the null hypothesis that all studies in the analysis share a common effect size. If all studies shared the same true effect size, the expected value of Q would be equal to the degrees of freedom, which is the number of studies minus 1. The Q value is 65.668 with 24 degrees of freedom and a p-value of less than 0.001. Using a criterion alpha of 0.1, we can reject the null hypothesis that the true effect size is the same in all these studies. The I squared statistic. The I squared statistic is 63%, which tells us that some 63% of the variance in observed effects reflects variance in true effects rather than sampling error. Tau squared and tau. Tau squared, the variance of true effect sizes, is 0.080 in logit units. Tau, the standard deviation of true effect sizes, is 0.282 in logit units. The prediction interval. If we assume that the true effects are normally distributed in logit units, we can estimate that the prediction interval is 0.097 to 0.269. The true effect size in 95% of all comparable populations falls in this interval. Please note that my intention here is not to have the program write the report. I'm simply trying to ensure that the statistics are interpreted properly. Along those lines, there is also an option to annotate this report and provide additional information. For example, if I click that option, the section on I squared would read as follows. The I squared statistic. The I squared statistic is 63%, which tells us that some 63% of the variance in observed effects reflects variance in true effects rather than sampling error. Notes on I-squared. There's a common belief that I-squared tells us how much the effect size varies across studies. In some cases, I-squared values have been employed to classify the amount of variation as being low, moderate, or high. While this interpretation of I-squared is ubiquitous in some fields, it's nevertheless incorrect. I-squared is a proportion and not an absolute amount. It tells us what proportion of the variance in observed effects reflects variance in true effects rather than sampling error. It does not tell us how much the effects actually vary. The statistic that tells us how much the effect size varies is the prediction interval, which is discussed below. Finally, the program inserts citations and references. The report can be exported to other programs such as Word. The core text is displayed in black, and the annotations are displayed in blue. Next, I want to create a high-resolution version of the forest plot. First, I'll modify this screen to specify which columns I want to display. For example, I'd like to display the number of events and the sample size for each study. To do that, I click this button, and the program adds a column with events over n for each study. Now I click High Resolution Plot. I click Reset All and choose Colors for Printing. I right-click on the title. I edit the title to read Mortality Following Mitral Valve Surgery in 80+. I want to modify the symbol for the prediction interval. I right-click anywhere on the plot. I click Study and Summary Symbols. I select the tab for Prediction Intervals. I click here to increase the line width, and I click here to add a cap at either end. I click here, and I modify the color. Next, I want to add additional space between the columns. I right-click anywhere on the plot. I select the tool for spacing and forest plot width. I select the tab for column spacing, and then I click the button with two blue arrows. I'd like to increase the width of the forest plot graphic. I select the tab for forest plot width, and I click the button with two blue arrows. The two sides of the plot are labeled favors A and favors B. These labels are intended for analyses that compare two groups, and they don't apply here, and so I want to hide them. I right-click on favors A, and I erase the labels for favors A and favors B. I'd like to send this to PowerPoint. I click File, Export to PowerPoint. The program opens PowerPoint and inserts the plot. In PowerPoint, I can annotate the plot, adding text, arrows, and so on. In PowerPoint, I can also display this full screen. Now I'll return to CMA. Back in CMA, I can choose colors for slides. I can modify any or all of the colors on this slide. And then I can send it back to PowerPoint again. Back in CMA, I choose colors for printing. If I wanted to, I could send this directly to Word. Or I could save it as a file and then import it into any other program. That's it for the basic analysis. This video continues in a moment, But if you're leaving us now, please visit our websites. This one has information about our workshops, and this one has information about the software. On either site, you can download a free copy of my book, Common Mistakes in Meta-Analysis and How to Avoid Them. When we analyze a primary study, we typically perform a sensitivity analysis. This means that we might perform a series of analyses to ensure that the results are robust. For example, we might want to ensure that the results were not overly influenced by one outlier. We can do something similar in a meta-analysis. Here, I'll outline some procedures that we might want to include as part of a sensitivity analysis. One issue we might want to explore is how much of an impact each study has on the analysis. Recall that the summary effect size is a weighted mean of the individual effect sizes. So we might want to see how much weight was assigned to each study. If I click this button, I can display a column with the relative weight assigned to each study. Initially, these bars are on a scale of 0 to 100. To see the weights more clearly, I can right-click here and choose Scale Relative to Maximum. This changes the scale so that differences among weights are easier to see. Additionally, I can sort by relative weight. I right-click on the weights. I select Sort from High to Low. We can see that no study gets more than around 11% of the weight. This tells me that I do not need to be concerned that any one study dominated the analysis. On the other hand, I see that there are 6 studies that each received less than 2% of the weight. And this will be important if I want to understand what the populations in the analysis look like. These 6 studies are listed as being included in the analysis, but actually played only a small role in our estimate of the mean effect size and the dispersion in effects. Now I'll resort the studies by effect size. Another type of sensitivity analysis is to ensure that the results are robust in the sense that the basic conclusions are not dependent on any one study. To look at this, we could run the analysis with only the first study removed, then with only the second study removed, and so on. CMA allows us to perform this sensitivity analysis with one click. First, I'll return to the data entry screen. By default, the studies will be sorted in the sequence on this page. I right-click on the event rate. I select Sort Low to High. I click Run Analysis. And now, by default, the studies are sorted based on the event rate from low to high. At the bottom of the screen, I have a tab for basic statistics and a tab for one study removed. I click on the tab for one study removed. Now, the row labeled De Gregorio does not show the results for De Gregorio. Rather, the row for De Gregorio shows the results for an analysis based on all studies except for De Gregorio. In other words, that's what we would see on the yellow line if we ran an analysis using the other 24 studies. The same idea applies to each row. What we see is that the mean effect size consistently falls between 0.16 and 0.17. In other words, the mean would not shift in any meaningful way if any one study were removed. I'll click Basic Stats to return to the standard analysis screen. Typically, at this point, we would perform an analysis to assess the potential impact of publication bias. While many meta-analyses of prevalence or incidence do include an analysis of publication bias, This is actually a mistake. When we're looking at the event rate in one group, it makes absolutely no sense to test for publication bias for the following reason. The basic idea of publication bias is that studies which are statistically significant are more likely to be published, and studies which are not statistically significant are less likely to be published. Since studies which are statistically significant tend to have higher effect sizes, the mean effect size in the literature will tend to overestimate the true mean. This idea might make sense when studies report statistical significance, but studies that report prevalence do not test for statistical significance. They simply report the prevalence. It makes no sense to say that studies which are statistically significant are more likely to be published when we're working with studies that don't report statistical significance. And for that reason, we will skip any discussion of publication bias here. We started with a look at the basic results, and then I took a tangent to discuss sensitivity analysis. We discovered that the basic analysis is robust, it is not dominated by any one or two studies, and the results are relatively stable. On that basis, let's return to the main results. The mean event rate is around 17%. On average, 17% of patients will die shortly after the surgery. But we also need to address the dispersion in effects. We discovered that the distribution of effects looks like this. At one extreme, there were populations where the risk of death was around 10%. At the other extreme, there were populations where the risk of death was around 27%. In this context, that's an enormous amount of dispersion. Consider a patient who's trying to decide whether or not to proceed with surgery. If I tell all patients that their risk of death is 17%, they'll need to make a decision based on that number. On the other hand, if I tell some patients that their risk is 10%, and I tell other patients that their risk is 27%, then each patient would be able to make a decision based on the number that applies to them. And in this case, that matters a lot. I suspect that many people would consider 10% an acceptable risk, but not 27%. The point is that when the event rate varies this widely, it becomes a key part of the results. It tells us that we cannot simply report the mean. Rather, we need to discuss the dispersion in effects and hopefully identify factors that are associated with the event rate. There are two procedures that we can employ to identify factors that are associated with the size of the effect. These are subgroup analysis and meta-regression. Here, I'll show how these procedures can be applied in this case. Let's return to the data entry screen. The columns over here hold data for variables that might be related to the event rate. This one is country. I double-click on the title country, and the column function is a moderator. We also need to specify the data type. The options here are categorical, integer, or decimal. We would use integer if this was something like year. We would use decimal if this was something like the number of hours required for the surgery. In this case, we're dealing with categories, so we use categorical. This column is labeled procedure. The procedure can be to either repair or replace the mitral valve, and each study is labeled either repair or replace. Studies that included some patients that had a replacement and others that had a repair are classified based on the majority. Again, we need to tell the program that this is a moderator variable. I double-click on the title procedure. The column function is moderator. And in this case, we're dealing with categories, so we use categorical. This column is labeled year. This is the year the study was conducted. And for multi-year studies, it's the midpoint of the study years. I double-click here. The column function is a moderator. The data type is integer. This column holds the proportion of cases within that study where the surgery was limited to the mitral valve alone. The column function is moderator. If these had been coded 0 to 1, the data type would be decimal. In fact, they're coded 0 to 100 with no decimal places, and so the data type is integer. This column holds the proportion of cases within that study where the mitral valve was replaced rather than repaired. This is a moderator, and the data type is integer. This column is based on the same data as this column, but this column includes the actual proportion of cases, whereas this one divided these into two categories based on the majority. Now we can save the file, and I'll return to the analysis screen. I click Run Analysis. If needed, I click Random Effects. As we discussed earlier, there are two lines here. This one deals with the mean, and this one deals with the dispersion in effects. For purposes of this tutorial, I'd like to focus initially on the mean effect size. So I'll uncheck the tool for prediction intervals. That hides the line with the prediction interval and leaves the line with the mean and its confidence interval. Next, I click Computational Options, Group By. The options displayed here are country and procedure, because these are the moderators that were defined as categorical. I select Procedure. I add a check mark to each of these options, and I click OK. I see that the studies are grouped as blank, repair, and replace. I want to remove the blanks. I click Computational Options, select by study name. On this panel, I click the tab for moderator. I choose Procedure, and I remove the check mark for blank. And I click OK. Finally, I'll right-click on the column with the event rate and sort from low to high. These are the studies where most procedures were to repair the valve. The mean event rate is roughly 11%. These are the studies where most procedures were to replace the valve, and the mean effect size is roughly 16%. To get a better sense of the difference between the two, I can hide the individual studies and display only the summary rows. To hide the individual studies, I deselect this button. And to make this easier to see, I'm also going to change the scale. Now the scale is 0 to 1. I right-click on the plot, I select Scale, and I click on 0 to 40%. For the repair studies, the mean event rate is 11%. For the replace studies, the mean event rate is 16%. I think it's clear that the difference is clinically important. And additionally, I can see that there is relatively little overlap between the two confidence intervals. And therefore, I expect that the difference in means will be statistically significant. We'll look at that in a moment. First, I'm going to reset the scale. And I'll click this tool to display the individual studies. Next, I want to ask if this difference is statistically significant. I click Next Table. This section is labeled Mixed Effects Analysis. This is the section that I want to use. I'll explain later what it means. The mean effect sizes are the same ones that we saw a moment ago. For the 6 studies that were based primarily on repair, the mean event rate is 11.4%. For the 15 studies that were based primarily on replacement, the mean event rate is 16.6%. To compare this mean versus this one, I can use a Q test. The Q value is 4.685 with 1 degree of freedom and a p-value of 0.03. For this test, we generally use a criterion alpha of 0.05. On that basis, I would reject the null hypothesis that the mean effect size is the same here and here. I would conclude that the event rate is higher here. So to recap, we've concluded that the difference between this mean and this one is statistically significant. I wanted to start with that conclusion, but in running these computations, I made a series of decisions. I need to discuss what those decisions were and why I made them. We also need to discuss what conclusions we can draw from the analysis and, equally important, what conclusions we cannot draw from the analysis. The first issue I want to discuss is the choice of a statistical model. As always, at the bottom of the screen, we can select either the fixed effect model or the random effects model. I selected the random effects model. Why? Well, when we're performing a simple analysis without subgroups, the difference between fixed effect and random effects is as follows. We would use the fixed effect model if we believed that all studies were based on the same population and were identical to each other in all important respects. In other words, if the true effect size for all studies fell directly on a vertical line and the observed effects deviated from that line only because of sampling error. The true effect size is the same in all studies because all studies are based on the same population. In that case, the results would apply to that population only and could not be generalized to any other populations. By contrast, we would use the random effects model if we believed that studies were based on different populations or varied from each other in meaningful ways. For example, the true effect size for the various studies might fall along this line, which is not vertical. What we're saying is that the true effect size varies from study to study because each study is based on a unique population. Critically, the random effects model allows us to generalize from the populations included in the analysis to the universe of comparable populations. As I've explained elsewhere, on that basis, the random effects model is almost always the one that we want to use. The same idea applies when we're using subgroups, except that now we apply the criteria within subgroups. And again, on that basis, the random effects model is almost always the one that we want to use. For example, consider the studies in this subgroup. If we believed that these studies were all based on the same population and were identical to each other in all important respects, we would use the fixed effect model to estimate the common effect size here, and that effect size would apply only to that one population. However, that is clearly not the case. While these studies are similar to each other, in the sense that they were primarily for mitral valve replacement, they are not based on the same population, and they do differ from each other in many important ways. Therefore, we apply the random effects model here, and this allows us to generalize these results to the universe of comparable studies. Similarly, if we believed that all of these studies were based on the same population and were identical to each other in all important respects, we would use the fixed effect model to estimate the common effect size here, and that effect size would apply only to that one population. However, again, that is clearly not the case. While these studies are similar to each other in the sense that they were primarily for mitral valve replacement, they are not based on a common population, and they do vary from each other in many important ways. Therefore, again, we apply the random effects model. And this also allows us to generalize the results to the universe of comparable studies. To select the random effects model within studies, we click this tab at the bottom of the screen. The next issue we need to address is how to estimate tau squared, the between study variance. This is the statistic that tells us how much the effect size varies across studies. In a simple analysis, when we have only one set of studies, we compute tau squared across all of those studies. But when we have subgroups, we must compute tau squared within subgroups. For the first set of studies, tau squared is estimated as 0.212. For the second set of studies, tau squared is estimated as 0.025. At this point, we have two options for how to use these estimates. One is that we can pool the two estimates. If we do that, we'll get a pooled estimate of 0.042. And then we can use that pooled estimate for both subgroups. Alternatively, we can apply each estimate to the corresponding subgroup. Since tau squared plays a role in the weight assigned to each study, the decision that we make about pooling will affect the values that we see here and here. The first option was to pool the two values and get one estimate, and then apply that estimate to both subgroups. And that would yield the numbers that I see here. This mean is 11.4% with this confidence interval, and this mean is 16.6% with this confidence interval. The second option is not to pool the two estimates of tau squared. Rather, we would use the value of 0.212 to compute the statistics for this set of studies, and we would use the value of 0.025 to compute the statistics for this set of studies. And that would yield the numbers that I see here. This mean is 10.9% with this confidence interval, and this mean is 16.9% with this confidence interval. In almost all cases, I want to pool the estimates. Why do I choose to pool the estimates? The reason is that an estimate of tau squared based on a small number of studies is not reliable. The estimate here is based on 6 studies and is not reliable at all. The estimate here is based on 15 studies and is not very reliable. So if we used the two estimates without pooling, these estimates would be relatively poor. By contrast, if we pool them, we have an estimate based on 21 studies, which is better. Obviously, when we pool the two values, we're losing information. That is, if the variance in effects for this kind of study is actually greater than the variance in effects for this kind of study, we lose that information when we pool. However, the amount of error that we introduce by pooling is likely to be much less than the amount of error we would introduce by estimating tau squared based on only 6 studies. And so this is the option that I've chosen here. How do I specify which option I want to use? I click Computational Options, Mixed and Random Effects Options. And in the top part of this panel, I choose the option to pool the two values. If you'd like to actually see the value of tau squared, click Next Table. The value of tau squared is displayed here. If I have selected the option to use separate estimates of tau squared for the first subgroup is 0.212, and tau squared for the second subgroup is 0.025. And these are the statistics that I would get for each group. On the other hand, if I have selected the option to pool the estimates, then tau squared for each subgroup is 0.042. And these are the statistics that we would get for each group. This is the option that I would use in this analysis. To this point, I've explained that we want to use a random effects analysis. Now I need to discuss why this is called a mixed effects analysis rather than a random effects analysis. The reason is that we need to choose a statistical model at two levels. Within subgroups, we're using random effects. That is, we use a random effects model to synthesize the data from these studies and yield these numbers, and we use a random effects model to synthesize the data from these studies and yield these numbers. At the same time, however, we're using a fixed effects model to select the two subgroups. The first subgroup is the one where most surgeries were repairs. The second subgroup is the one where most surgeries were replacements. The two subgroups are fixed. The word fixed here does not mean that the two groups are the same, since obviously they are not. Rather, they are fixed in the sense that they have been selected or identified. In other words, we care about these specific subgroups only. We want to know the mean effect here and here. We will not be generalizing from these two subgroups to any other subgroups. Indeed, I can't even think of what those other subgroups might be. To specify that we'll be using fixed effects for the subgroups, I click Computational Options, Mixed and Random Effects Analysis. And this selection is made on the bottom part of the panel. I select the option to combine subgroups using a fixed effects model. So, to recap, we'll be using the fixed effects model to identify the specific subgroups that we care about. We set that here. And we'll be using the random effects model within subgroups. We set that here. Since we're using fixed effects at one level and random effects at the other, this is called a mixed effects model. I discussed this further in my workshop, but these are almost always the options that you'll want to use. Now let's return to the key finding. The difference between this mean and this one is statistically significant. What does that tell us? The answer is probably not what you'd expect. I am able to say that the effect size here was greater than the effect size here. However, I cannot say that this is due to the fact that these surgeries were primarily repairs, while these were primarily replacements. Let me say that again. I can say that the effect size is higher here than here, and that the difference is statistically significant. But I cannot say that this difference is due to the fact that these were repairs while these were replacements. This may seem counterintuitive, so let me unpack this. As we saw a moment ago, the difference in means is statistically significant. So we can say that the risk of death was higher in these studies than it was in these. But we cannot say that the type of procedure is responsible for the difference. And the reason is that we did not use a random process to assign studies to use replacement versus repair. Therefore, we need to be concerned that there might be other variables which are confounded with the type of procedure. For example, suppose that the studies that repaired the valve tended to enroll patients who were younger, closer to 80, while studies that replaced the valve tended to enroll patients who were older, closer to 90. We chose to call these groups repair versus replace, but it's possible that a more appropriate label would have been younger versus older. In other words, it's possible that age, rather than the procedure, is responsible for the difference in means. Similarly, it's possible that studies which employed repair tended to be based on healthier patients, while studies which employed replacement tended to be based on sicker patients. And it's possible that the patient's health, rather than the choice of procedure, is responsible for the higher death rate that we see here, and so on for any other potential confounds. The key point is that the difference between subgroups is almost always observational rather than causal. So we can say that the mean risk was higher in studies that employed replacement, but we cannot say that this is due to the use of replacement rather than repair. It might be due to that, but it could also be due to some other factor which is confounded with the type of procedure. If we have enough studies in the analysis, it might be possible to use meta-regression to try to isolate the impact of procedure separate and apart from any confounds, but we're not going to talk about that now. There are two more points that I'd like to make before moving on. This is the mean effect size for studies that used repair. This is the mean effect size for studies that used replacement. And this is the mean effect size across all studies. We need to ask if it makes sense to report this value. In some cases, it will make sense to report this value, and in some cases, it will not. But it's important to understand what this value represents. The mean here is a weighted mean of this mean and this one. Since this subgroup has more studies than this one, it will tend to carry more weight in computing the overall mean. The mean effect size here can be thought of as the mean effect size in the universe, where roughly 30% of the studies employed repairs and roughly 70% employed replacement. I'm not sure that this is a universe that I would care about, and so I might choose to remove the line with the overall effect size. To do that, I deselect this button, and the overall effect size is now hidden. However, there are reasons that we might want to display the overall mean. If the only factor relevant to the event rate was the type of procedure, and we have these two estimates, then indeed it might be best to hide the overall mean. But that isn't the case. The overall mean depends not only on the procedures used in the different studies, but also on the ages represented in the different studies, on the year when the different studies were performed, and on an extensive array of other potential moderators. The overall mean is a summary statistic that incorporates the impact of all these moderators. Put another way, if the mean in these studies is being used to make an inference about the mean in the universe of all comparable populations, then the overall mean serves that purpose. And for that reason, it might be useful to display it. The second issue is the following. When we compare subgroups, it's common to focus on the mean and to ask if the mean in one subgroup is different than the mean in the other. When we test for statistical significance, we're comparing the two means. However, from a clinical perspective, we also need to think about the overlap between the two subgroups. To see that, I can click here and once again display the prediction intervals. For repair, the risk in various populations ranges from 7% to 19%, and for replacement, it ranges from 11% to 24%. So there is a fair amount of overlap between the subgroups, but also an important amount of non-overlap. That's a basic look at subgroups analysis. We just looked at the type of procedure as a potential moderator. The other potential moderator we want to look at is year, that is, the mid-year of the study. Since year is a continuous variable, we cannot use subgroups analysis to look at its relationship with event rate. Instead, we'll use meta-regression. First, I need to remove the subgrouping. I click Computational Options, Group By, and Reset. Then I click Analysis, Meta-Regression 2. This frame shows all the moderators I had identified on the data entry screen. Note that these include both continuous and categorical moderators, since both can be used in a meta-regression. I click on Year. I click Add to Main Screen. And the program moves year from here to here. Close this panel. I add a check mark for year, and then I click Run Regression. This table reports the statistics. I'll come back to that momentarily, but first I'd like to see a plot of the data, which will provide some context for understanding the statistics. I click Scatter Plot, and the program switches to this screen. The title is Regression of Logit Event Rate on Year. The x-axis is year. The years range roughly from 1985 to 2005. The y-axis is the event rate in logit units. The regression line moves from the upper left to the lower right. A logit value of 0 would correspond to an event rate of 0.50. A logit value less than 0 would correspond to an event rate lower than 0.50. So the risk decreased over time. In 1985, the predicted risk is roughly 22%. In 2005, the predicted risk is roughly 11%. But this plot is in logit units, so how do I get these event rates? The answer is I do that in Excel. To get the predicted event rate in 1985, the formula is 82.52 plus 1985 times minus 0.0422. And that yields minus 1.25, which is this point over here. To get the predicted event rate in 2005, the formula is 82.52 plus 2005 times minus 0.0422, and that yields minus 2.10, which is this point over here. So these are the values here and here, but they are in logit units. To convert the logit units into proportions in Excel, if the logit value is in cell A1, we would use the formula equals exp parentheses A1 close parentheses over parentheses exp parentheses A1 close parentheses plus 1 close parentheses. So for 1985, the event rate is 0.22, and for 2005, the event rate is 0.11. Now let's return to the main results screen. This table shows me the relationship between event rate and year when all other variables are held constant. In this case, the only variable in the equation is year, and so this is simply the relationship between event rate and year. As we move from one year to the next, the expected risk drops by 0.04 logit units. Since it's not easy to make sense of this in logit units, we looked at the plot and translated these numbers into event rates. And we saw that between 1985 and 2005, the predicted event rate dropped from 0.22 to 0.11. We can also test the null hypothesis that there is no relationship between year and event rate. In other words, that the true coefficient here is 0. The z-value for that test is minus 2.53, and the p-value is 0.0113. If we're using a criterion alpha of 0.05, we would reject the null hypothesis that there's no relationship between year and event rate. where the table at the top provides information for each covariate with all other covariates held constant. This table provides information for the full set of covariates. Put another way, this asks if all the covariates as a set are able to explain any of the variance in effect size. In this case, since there's only one covariate in the analysis, this analysis is the same as this one. This analysis uses a Q value rather than a Z value. The Q value is 6.41 with 1 degree of freedom and a p-value of 0.0113. Since there's only one covariate, this p-value is addressing the same null hypothesis as this one, and the two p-values are therefore the same. The part of this section we just looked at addresses the question, do the covariates explain any of the variation in effects? The second part of this section asks if the covariates explain all of the variation in effects. To explain what the second part means, let's have another look at the plot. We have the regression line, and we have the individual studies. The null hypothesis being tested in the second part is that year is able to explain all of the variation in effects. Put another way, the null hypothesis being tested is that the true effect size for all studies falls directly on the regression line. Of course, most of the observed effects fall some distance from the regression line, but the null hypothesis refers to the true effects rather than the observed effects. The null hypothesis is that the true effect size for this study is actually here. The observed effect size is here only because of sampling error. Similarly, the true effect size for this study is actually here, and the observed effect size is here only because of sampling error. And so on for all the other studies. To test this null hypothesis, we use a Q value. Q value is 34.36 with 19 degrees of freedom and a p-value of 0.0166. By convention, we use a criterion alpha of 0.1 to test this null hypothesis. Since 0.01 is less than 0.10, we would reject this null hypothesis and conclude that year does not explain all of the variation in effects. Taking these two elements together, we conclude that year explains some of the variation in effect size, but not all of the variation in effect size. Similarly, there is a statistic here called the R-square analog, which is 12%. This tells us that year is able to explain roughly 12% of the variation in true effects. Notice that the statistic is called the R-square analog because it's analogous to the R-square statistic that we use in multiple regression in primary studies, but does differ from that statistic in some important ways. To this point, I've been using the z-distribution to compute the confidence intervals and the p-values for the coefficients and for the overall omnibus effect. However, it's generally a better idea to use the Knapp-Hartung-Siddick-Yankman adjustment. This adjustment yields a confidence interval and a p-value that tends to be more accurate than the one we get using the z-distribution. To do that, I click Computational Options, Knapp-Hartung. Now, this table shows us the adjusted confidence interval, a t-value rather than a z-value, and an updated p-value. Similarly, this table shows us the f statistic rather than the q value and an updated p-value. This was intended as an overview of the Meta-Regression module. In my workshops, I go into a lot of additional detail. For a more extensive discussion of meta-analysis, consider subscribing to our workshops, which are now available online as well as in person. For information, visit metaanalysisworkshops.com. This is also where you can download a free copy of my text, Common Mistakes in Meta-Analysis, and How to Avoid Them. In this video, I used the software Comprehensive Meta-Analysis. For information about the software, please visit metaanalysis.com. My name is Michael Borenstein. My email is biostat100@gmail.com, and please feel free to contact me with any questions or comments. Thank you.